Hello everyone and welcome once again to my channel. In today's interesting class, I'm going to walk you through a question on the principle of homogeneity. The question looks very difficult to most people, but trust me, it's something that we can always solve. The question reads, the velocity v of a particle varies with time. According to the relation, v is equal to wt squared plus xt plus y. Okay, now here are things that you need to understand. The first thing that you need to do is that you must identify the given variables in the question. And then the next thing you have to do is to find their dimensions. The given variables are velocity and time. These are the ones that we can easily find their dimensions. And with these ones, we can find the dimensions of w, x, and y. First, what is the principle of homogeneity? The principle of homogeneity states that expressions or units on both sides of an equation must be the same. If that is true, then it means that we can equate velocity to wt. Let me show you what I mean. So we say based on the principle of homogeneity. Okay, so based on a principle of homogeneity, we can easily equate everything to v since both sides are equal, right? So we say v is equal to wt squared. The same v is equal to xt, and then lastly, the same v is equal to y, based on the principle of homogeneity. If truly velocity is equal to everything on the right, then it means that it's also equal to them when equated separately. You see, velocity is on the left. It's equated with everything on the right. If it is true, or if velocity is truly equal to everything on the right, then it's also equal to them when equated separately, just like as I have done right here. You can see it. V is equal to wt squared, v is equal to xt, and v is also equal to y. At the end of this solution, I am going to verify my working to show that it is correct. If it is correct, then it means that the dimensions are true. If my solution is not correct, it means that something is wrong with either the equation or my solution. Now let's get right into it. So the first one, v there, is velocity, as written in the question, that the velocity of a particle varies with time. So we were only given velocity and time. Now, how do we find the dimension of velocity? Velocity, v, is measured in meters per second. Okay, this is the SI unit. If you want to get the dimension of any physical quantity, you can either use the formula or the SI unit. In this case, I'm choosing the SI unit to as a step for finding the dimension. Now, this on top is meter. This is meter, which is m, and meter is the SI unit for length. Okay, meter is the SI unit for length. And then the dimension for length is just L. We got this from the first three fundamental quantities, which are mass, length, and time. So the M represents the dimension for mass, the L represents the dimension for length, and the T represents the dimension for time. There are 7 physical of fundamental quantities, but then we use mostly the first 3 for dimensioning. Now, since we've determined that the dimension for length, which is measured in meters, is L, this now becomes L over, for S, it is second, right? So second is a unit of time, and the dimension for time is T. Okay, so we have now determined that the dimension for velocity is length over time, or let's say L over T. Now, we can make this to appear more stylish by taking the t away from the denominator. So when you take it up, it now becomes LT minus 1. Now, this is using the reciprocal law of exponents, where it says if you have 1 over a, okay, remember that this a here has the power of positive 1, just like our t down here had the power of plus 1. So when you take away this a to the power 1 from the denominator, it now becomes a to the power negative 1. So if it were a positive 2 down here, when it goes up, it becomes a negative 2. If it were a negative 2 down here, if you take it upwards, it becomes a positive 2. Okay? It becomes a positive number. Now, we found the dimension for velocity, which is Lt to the power minus 1. Now, the next one there, which we are given, is t. So for t is just time. And the dimension for time is capital letter T. So we can now go ahead and solve, having found the dimensions of these given variables. Now let's begin. So the first one that we had, we said that V is equal to WT squared. This is gotten from the relation. You can see it here. Okay, velocity is equal to WT squared, and I have to equate them separately. Right here, you can see them. This is our equation 1, this is our equation 2, and here we have our equation 3. Okay, now we've determined that velocity is giving us Lt to the power minus 1, and now this is equal to W. Then for the dimension for t, we have it for time, we have it to be t squared. Remember that the t here is a squared, so whatever be the dimension would also be squared. Now, how do we do this now? In order to determine the dimension of W, we simply divide both sides by t squared. We divide both sides by t squared. So this t squared cancels out with the 1 on the right, and we now have that W is equal to Lt minus 1 over t squared. Okay, so we can now simplify this expression to the expression on the right. This one is on the right. So we can simplify it to determine the dimensions of W. Therefore, we have that W is equal to, so I'm also going to apply the same reciprocal law of exponents by taking the t to the power of 2 upwards. I'm going to remove it from the denominator, and you know that if it goes upwards, it's going to become a negative. Therefore, we have Lt minus 1. When it goes up, it becomes t minus 2. Okay, now we are also going to apply another law of exponents that says if you have like bases, for example, a times a, you can see that this right here is a base, and this here is a base. The a's are bases, and we can see that we have this one is to the power of 2, and this is to the power of 1. So the law says if you have like bases that are multiplying each other, please add their powers. Okay, so this only applies when they are multiplying. When they're adding, they don't, this law does not work. When they are subtracting, the law does not work. It only works when they are multiplying. Now, we also apply the same concept. We have W is equal to LT. Then since we're going to add the powers, because this L multiplies the T and the T multiplies the T, so we can now add the powers by having minus 1 plus minus 2. Okay, so just like when you press on your calculator, minus 1 minus 2, or you can also say minus 1 plus minus 2. So minus 1 plus minus 2 gives you minus 3. Therefore, the dimension for W is now Lt to the power minus 3. Now we found this one. Let's now go ahead and find for x. So for x, we derived equation 2, which was V is equal to xt. Okay, you can see it here. This is our equation 2 right here, and we're now going to solve it to see what we're going to obtain. So to solve for x right now, I'm going to simply divide both sides by t. Let me make it shorter. So we divide both sides by t. The t is the cancel out. We now have that x is equal to velocity over time. Okay, now let's go ahead and solve for the dimensions of x. So we say that x is equal to, we determine the dimension of velocity to be L t minus 1, and this is over. The dimension for time is simply t. Applying the same reciprocal law, I'm going to move this t to the power of 1 from the denominator upwards, and when I move it, it's now going to be x is equal to lt minus 1, which is the one we have already. And then when we take the one that's at the denominator up, it also becomes minus 1. Therefore, we can also apply the same multiplication law of exponents that says if you have like bases that are multiplying, you simply add their powers. Hence, we have lt minus 1 plus minus 1 gives you minus 2. So this is the dimension for x. Now, let's solve for the last one, which is the dimension for y. Our equation 3 says that v is equal to y. Correct. Okay, so v is equal to y. Now, this implies that the dimension for v is also the same with y. There is no difference. Therefore, we say lt to the power minus 1 is equal to lt lt to the power minus 1. Okay, so, or we can say that since our v is lt minus 1, this is equal to y. Therefore, y is equal to lt to the power minus 1. All right, so these are their respective dimensions. We determine x to be lt minus 2, as you can see right here. We found w to be lt minus 3, and we found y to be lt minus 1. So these are the dimensions. Now the question right now is, how am I sure that these truly are their dimensions? We can verify by plugging them back into the equation to see what we're going to get. Let's just try it and see what we're going to obtain. Here we have the equation to be v is equal to wt squared plus xt then plus y. Let's try and see what we shall obtain. On the left hand side, we have lt minus 1, which is the dimension for velocity. This is equal to, for the w, we determined it to be what? lt to the power minus 3. And then we have a t. The dimension for t is just t squared, okay? The dimension for time is just t, and since it's squared, we also square it. Then this is plus, the dimension for x was determined to be lt minus 2, and we also have a t, which is time, so this gives us t. And lastly, we have plus lt minus 1. Remember that the dimension of y was determined to be the same thing with velocity. So let's now simplify and see if what we have on the left will be equal to what we have on the right. If that is true, then it means that we are correct, okay? So on the left hand side, we have lt minus 1 is equal to, right here, I'm going to remember the laws of exponents that says if you have like bases that are multiplying, you simply add their powers. So we have lt, then we have minus 3 plus 2, okay, minus 3 plus 2, correct? Then we have plus, down here we have, or here we have lt, we have minus 2 plus 1, then plus lt minus 1. This one is already in its simplified form, so we're not going to work on it. Here we have lt minus 1 is equal to, so let's add this to minus 3 plus 2 gives you a minus 1. Therefore, we have lt minus 1 plus, for this one here, we have minus 2 plus 1 gives us lt minus 1. Then plus lt minus 1, which is this one here. Okay, so you can see that we have lt minus 1, lt minus 1, lt minus 1. They are adding, so we can add them together, just like when you have x plus x plus x. They are just like terms, so we can add them together. Therefore, we have lt minus 1 is equal to, this one is 1, this is 2, this is 3. So we say 3lt minus 1. But then, in dimensional analysis, constants are dimensionless. When I say constant, I mean numbers like 3, pi, 2, 7, any number, okay, is a dimensionless constant. So we can now delete this one. We can eliminate it by throwing it away since it does not have any dimension. And we are now left with LT minus 1 is equal to LT minus 1. Have you seen that the principle of homogeneity holds true in this case? And this simply means that truly the dimensions of 4W is truly LT minus 3. The dimension of X is truly LT minus 2. And then for Y, it is truly LT minus 1. Thank you for sticking around till this point. In our next video, we shall be talking more about dimensional analysis. Please do not miss it. Thank you and bye.